The topic we've looked at recurrent neural networks so far, and how they can be used to analyze time series. The topic that we will embark on in the next couple of lectures uses recurrent neural networks of various kinds to address a very important problem, sequence to sequence modeling. Now this is a generalization of the problems we've seen so far. The idea is that a sequence of input comes in, a sequence of output goes out. So speech recognition, for instance, a sequence of audio vectors comes in, a sequence of words comes out. Machine translation, a sequence of words comes in one language, a sequence of words goes out in another language. So our dialogue systems, the user says something, it's a sequence of words. The system responds, it's a sequence of words. It's exactly the same problem. Or question answering, a sequence of words comes in, it's a question, and an answer comes out which might either be brief or which might be a sequence of words. So all of these they look like very different problems, but they're basically fundamentally a case of sequence to sequence modeling. Now in general, the number of symbols that goes in may not be related directly to the number of symbols that comes out. So there doesn't have to be any kind of either order or time synchrony in the input and out between the input and the output. So here are the two variants, right? Speech recognition, there's a sequence of vectors or samples that goes in. If you're working directly off the speech signal, then you would be getting 16,000 samples per second, or maybe all the way up to 44,000 samples per second. And the number of output symbols would be 4 or 5. Or if you're thinking of it in terms of phonemes, maybe up to 10, but not a whole lot more than that. So there's a great difference in the size of the input and the size of the output. The output and input are order synchronized, as we saw. Or if you've got something like machine translation, in goes I ate an apple, and out comes a Shaba and an Apfel gegessen. Now observe something interesting here. The output order is not the same as the input order. So the word I goes to ish, 8 goes to gegessen, but then an is einen, apple is Apfel, but there are actually 5 words in the output. So the output is longer than the input, and in fact the word ate goes to habe gegessen, which I ate, right? So there's neither order synchrony nor time synchrony, nor indeed any predictable relationship between the length of the output and the length of the input, or a necessarily predictable relationship between the two. We saw this first case, and this is what we're going to talk about today, where we had order synchrony. The input and output sequences happen in the same order. They may be time asynchronous, meaning you don't have the same number of symbols in the output as in the input, but they are order synchronous. Can you just follow Piazza just in case? Yeah. So this would happen, for instance, in speech recognition. A simple variant of it is this one, where you have a sequence of inputs going in, and a single symbol coming out. We saw this. So a sequence of speech vectors goes in, and a single classification output comes out. When we train for something like this, the only place where you actually have any notion of error is when you get the final output, so which is at the final time instant. So that is the only place where we can actually legitimately define a divergence, and the derivatives of those divergences, that divergence must be fed back to update parameters everywhere. We saw that we could try to exploit a little more of the structure of the problem. Observe that the network actually produces outputs at every time. And so you're not restricted to using just the output at the final time. You could pretend that at the other times too, you wanted the same output as you would get at the final time. And now you can compute divergences everywhere. And you can now compute a divergence between the input and output target sequences as a weighted sum of the localized divergences at each time. And typically the localized divergence you would use is the cross entropy. So the weights, of course, would depend on the problem. So if you are doing something like speech recognition, it's reasonable to assume that all the weights are 1. if you're doing something like question answering, it is not reasonable to assume that the answer must be provided before the question is complete. So in this case, the weights are going to be biased towards the end. So training over here, you could just define the divergence everywhere, and you could pass the gradients through the network. All of this we saw. Then here was the more complex version of the problem, where you're given a sequence of inputs, and you must asynchronously output a sequence of symbols. So this is just a simple concatenation of many copies of the simpler problem, output at the end of the symbol sequence problem. But this simple concatenation made things really complex, in the sense that both during decoding and, thank you, my trusty pointer, right? So both during decoding and during training, you would not necessarily know exactly where these symbols must be output. So in fact, the network produces outputs at every time, and at some single instant of time, the output is actually what you want to see. The rest of them are kind of spurious. And it's hard to know which of these is the actual output. So if you were performing inference using this network, if you're trying to compute outputs, what you would actually get was something of this kind, where at each time there's a complete probability distribution over all the symbols, and you'd have to figure out, and most of these are, most of the symbols are kind of bogus, and only some of these symbols are required. So now one way to think about this is that you actually want to produce something like this, where the symbol sequence that you want to produce is the one that is most probable for the given input. Now remember, we've said this from the first class. What the network actually produces is a posterior probability over the classes given the input. So in this case now, the classes are symbol sequences, and you want to find the symbol sequence that is a posteriori most likely given the input. So the actual task you want to perform is to compute the most likely symbol sequence over the inputs. And now the problem is that the output symbol sequence can be of any length, some k. The input symbol sequence inputs could be of a different length, n. And you need to find out the most likely symbol sequence of some unknown length given the input symbol sequence. Now at this point, for today's lecture, we're going to assume that the number of symbols in the output is, first, that the output is order synchronous with the input, and secondly, that the number of symbols in the output is not greater than the number of vectors in the input. So k is lesser than or equal to n. So under this, here's a very simple thing we could do. We could simply pick the most likely output at each point. And if you pick the most likely output at each point, then the product of their probabilities is going to be fairly high. And so you'd get, and so you would approximately pick, and then once you've done this, you can just merge all repetitions of a symbol. And thereby, the hypothesis is that the final instance in the repetition is the actual symbol you want to output. And you can be somewhat confident that this symbol sequence is indeed the most likely symbol sequence. Now I'm saying somewhat confident as opposed to sure, even though you're picking the most likely symbol at each time, and there is a reason for this. And we will get to this reason in a few minutes, okay? Now the problem here, of course, is that we cannot distinguish between repetitions of this kind, and also the output may be meaningless, right? We have no constraints. So you could try to impose external constraints like only allow sequences that are correspond to dictionary words, or allow only certain sequences of sub-symbols like we saw in here in homework 1. That it doesn't really matter. We'll get back to the problem in a bit in detail. But this whole process of obtaining an output from the network as part of inference is what we will call decoding. And you're going to see this term decoding a few times. Now, the fact that I said that you can be somewhat confident that this is the most likely symbol sequence, there's a reason for it. The reason is that what you're really looking for is a order synchronous but time asynchronous output. And what this is giving you is a time synchronous output. So to explain, let's say you have 5 symbols in the output. You have, say, 5 vectors in the input or 6 vectors in the input. So you have x1, x2, x3, x4, x5, x6. Then you could have something like AAA, BBB, and this represents the sequence AB. But you can also have AA, BBB, B, and this also represents the sequence AB, right? So if this, and then I could have something which is CC, C, D, D, D. And this represents the sequence CD, right? If of these 3 sequences, if this sequence were the most probable, this algorithm is going to pick up this sequence, and the actual output sequence that you'd produce is CD. But then consider this. There are 2 sequences for AB, 2 extended sequences for AB, both of which collapse to the reduced symbol sequence. So both of these collapse to this symbol sequence. So the actual probability for AB is at least going to be the sum of these 2 guys. And that sum may be greater than the probability of this individual sequence. So when you actually just pick the most likely sequence at any time, you would end up getting the most likely order synchronous sequence, but not necessarily, I mean, a time synchronous sequence, but not necessarily the most likely order synchronous sequence, right? And so this is just an approximation. But in any case, we've sort of seen how we have some idea of how we can decode the output of this network, perform inference. The bigger issue that we'll spend a lot more time on is training. Now, how do you train this network? If you're given output symbols, in your training data, you're going to be given sequences of inputs. You're going to be given sequences of outputs. So if I'm given the sequence of inputs, and I'm informed exactly where in the output, where in time each of the outputs was produced, then so here, for example, if the word I'm looking for, this input speech corresponds to the word beefy, right? And then if I were informed that the phoneme B ends at the 2nd time instant or 3rd time instant, E ends at the 5th, F ends at the 7th, and E ends at the 10th. There are 10 inputs over here, 0 through 9, right? If this this information were given, then all I really need to do is to compute the outputs of the network at those 4 time instants. And then compute the divergences at those 4 time instants. And it's only these divergences that are actually going to contribute to the overall divergence between the desired input and the target output. Now this, of course, is kind of wasting the information that you're producing at the intermediate stages. And because you're wasting the information that you're producing at the intermediate stages, an easy fix is to pretend that at the intermediate stages, the symbol that you really want, you should ideally be producing the same symbol as you would at the terminal segment of a terminal input of that segment. And now you have a complete sequence of target outputs, although this is synthetic, right? And now you can actually compute a divergence, which is going to be, in our simple case, just the sum of the divergences at the individual time instance. And now keep this in mind, this is important. If I'm using the cross entropy divergence, and if I'm representing the output as a one-hot vector, then this simply becomes the sum or negative of the sum over all time of the log of the probability assigned to the target symbol at each time. We've seen this several times, right? So this is not really a mystery to you. Now, I wish I had my clicker. If I compute the derivative of this divergence with respect to the outputs at each time, then the derivative of the divergence, remember when we wanted to train a recurrent neural network, the first step you needed was the derivative of the divergence with respect to each of the outputs. Once you had it, the rest of backpropagation was fairly straightforward. So the key problem challenge now really is how do you compute this derivative? This is what we're really focusing on. And that derivative over here, if I define things in this manner, the derivative of the divergence with respect to the output at each time is simply going to be a vector of zeros except this one component, which is the component corresponding to the target symbol, and that one component is simply going to be -1 over the computed probability for that symbol. Now this looks just like your standard cross entropy divergence when the target is 1 hot, right? So far so good. The issue really was this. Suppose I didn't give you information about where the output symbols happened. Now how would you compute this divergence? So can anybody take a guess? Any suggestions? Yes?
I think you use like the encoder decoder, kind of like you use for like translation.
You're way ahead, right? And to be honest, I'm not even sure what, how clear you are or what you're saying. Something very simple. Can you give me a simple suggestion?
Rather than considering all symbols, we can consider just these 4 symbols.
There are only 4 symbols. Where are you going to place them, right?
Could we just see until when we were seeing y and then
So here I'll give you a very simple suggestion. These are all iterative learning algorithms, right? I can assign an initial alignment. So what we are really computing is an alignment, right? This term alignment is going to pop up a few times, but I have x0, x1, x2, x3, x4. My indexing keeps varying through my slides, bear with me. And then I have the symbols S1, S2, S3, which could be something like B, beam, right? So if I want to do this, I'm trying to align this sequence of 3 symbols to the input, which is like saying, I'm going to say that these guys are all B, this is E, and these are all M. So I'm actually sort of figuring out how much is B, how much is E, and how much is N. So this is an alignment of the target symbol sequence to the input, right? So I can start off with an initial assumed alignment, and once I have an initial assumed alignment, I can train my model because I know exactly how to compute the derivatives. The derivatives are easily enough derived, and then I can go ahead and train my complete model using this initial completely randomly suggested alignment. And once I've trained the model, I can go ahead and decode with this. I can re-estimate the alignment given the trained model, and then I can use this re-estimated alignment to go back and train my model again. So I've started off with, say, this alignment, right? And once I use this alignment, I can train a model, and I have some model which is going to presumably not rubbish. I can use this rubbish to recompute this alignment, and the recomputed alignment might be different. So the second round, it might be something like, something like that, which is going to be different. I can use this re-estimated alignment and then go back and train my model. Problem? I've hidden a lot of crimes in this one sentence, re-estimating the alignment. How exactly do I re-estimate the alignment given the input symbol sequence? So the problem here is this. The problem, you have an unaligned k-length symbol sequence, S0 through sk minus 1. You have an input, which is these guys. You have an input of some length n, which is these guys, right? And you must figure out how many times to repeat each symbol to match the lengths of the two. That's basically the problem of the alignment. So I'm taking a k-length symbol sequence and expanding it out to an n-length symbol sequence by repeating symbols. And I have to figure out the best way to do so. Now here's something, here's a trivial way of trying to do this. I can just go to my computer, I can, let's say I've trained my model. I could just compute the output probability table. I'm going to get probabilities for every symbol at each time. And then I can just pick the most likely output at each time, and I can call this my alignment. Will this work? Anyone? Why not? It's obvious, it's staring you in the face, right? It's on the slide. The target output over here is, if I were looking for the word beefy, is this really the word beefy? No. Because when you just pick the most likely symbol at any time, you could be picking pretty much any symbol. You're not constrained to be picking only the symbols that you really have in your output sequence. Suggest a solution. So if I could just do that, I can just say, okay, I'm going to knock all of these guys out, blank all of these guys out. So these are the only symbols that I have left. So I started off with my original table. I yanked out just the rows corresponding to the symbols that I'm interested in, compute a reduced table, and then I can pick the most likely symbol at each time from this one. Will that work?
No.
Why not?
First one you can only have in the
Exactly, right? If I just go ahead and if I only decode on the reduced grid, I can end up with something of this kind, which is beef, whatever, some rubbish. You never know. You have no additional constraint that once a B has occurred, it can never be revisited, right? So how can I fix that? I'm still going to be using something very simple, right? How do I fix that? How do I ensure that once I've produced an initial B, I don't produce a B again?
We should know all of the possible sequences that can occur at a particular time step.
Right.
And if we know that, then we can constrain our search to have only those which are possible. Like for the first one, only B is possible. And for the second one, if the B has occurred, then B and
Yeah, but there's a very nice mechanical way of doing this, right? And the mechanical way of doing this is that I'm going to make as many rows in my table as the number of symbols that I have in my target output. So here I have beefy. So I just pulled out the B row and stuck it as my first row in my table. The second row is my row for E. I stuck it as my second row. The third row, I stuck it out as, I pull out the fur. The fourth, I pulled out E again. Observe that the reconstructed table over here actually has this character E, rows for E occurring twice. So I've got the reduced table, but this reduced table has one row per output target symbol. And if symbols occur multiple times, I'm going to get the rows multiple times. And now, so I keep introducing pseudocode in the slides. I won't actually be going over the pseudocode myself. Take a look, because the pseudocode is actually very informative, right? And now I have a table, and then I can say I want to find a path from the top left corner to the bottom right corner, where as I travel through the boxes, I'm only allowed to travel forward or forward and down. So either a horizontal step or a one step down diagonally. And this ensures that I'm going to follow a path which actually gives me a valid instance of beefy and nothing else, right? And so this guarantees that the sequence is an expansion of the target sequence. The way I can do this is by explicitly imposing this constraint and the arrows show the steps I can take. So these are the only, I have to start at the top left corner, and I can only follow one of the arrows going out of any box, and eventually I'm going to end up at the bottom right corner. And the path I've taken is going to be a valid alignment. Now I will assign a probability of 1 to taking to each of the arrows, just as a kind of engineering solution. And I'm going to assign the probability of the symbol to each node. So then if I do so, this whole thing just becomes a graph where every node in the graph has a score, which is the probability of assigned to the symbol corresponding to that row at that time by the network. Every edge has a probability of 1. And now any path will have a score which is the total probability of all the symbols in the path. So the path, this path over here, y0b, y1b, y1b, y2e, y3e, y4f, that path will have a probability, which is simply the product of all of those y's, where the y is simply the probability assigned to the symbol at that time. So for instance, y2e is the probability assigned to the symbol e at time 2 by the network, right? Remember that all of these probabilities have already been computed. And so, and a typical end-to-end path is going to have a complete chain, a path through this graph, and it will have a score, a probability. But then do I want just any path? What am I really looking for? I'm looking for the most probable path, right? And the most probable path, there are any number of, can you give me some algorithm which would find the most probable path from the top left to the bottom right? What is that? Expand that. Depth first search. Actually, yes. Or something else?
At every node, you only look at the maximum of the nodes that is coming into it. That way you can cut down on
the dynamic programming, right? Basically. That's basically what we call the Viterbi alignment algorithm, right? Depth first search is definitely one of the solutions. But in this kind of, because the thing is so nicely, cleanly structured, a Viterbi algorithm is probably going to be much more efficient because a depth first search really has no upper bound, no real tight. In the worst case, you can end up searching all paths. And you want to keep the computation fixed. So here's what we're going to do. We want to find the most probable path from source to sink, and we will do this using a dynamic programming algorithm. And this is the Viterbi algorithm. Here is the basic idea behind the Viterbi algorithm. Now if you want to find the best path, most likely path, from the source to the node yf3. yf3 has only two parents. The blue box just above, y2e and y2f, right? So this guy has only 2 parents, those 2. And if I assume that I already know the best path to each of these 2 parents, then the best path best path from the source to this guy has to be an extension of one of these best 2 paths, right? So basically, it's either going to be y0b, y1b, right? y2e is it? And y3f. So this is so the best path is either going to be this guy with this probability, or the other one was y0b, y1e, y2f, y3f. So how do I pick how do I pick among these 2? I just pick the path which has the higher probability, right? Because I know the paths, and so I know their probabilities. This last term, of course, doesn't have to be considered. I just need to pick the best of these 2 guys. And if at each time I assume that I actually know the entire sequence and the probability of the sequence, and that I've stored it at the end of the path. I just need to look at the immediate parent, decide which is better, and then extend it. So this gives you a very simple algorithm. The best path from the source to any node in the graph is going to be the extension of the best parent, where the best parent is simply going to be the parent for whom the best path probability is highest. So it looks kind of ugly, but if you actually write it down in code, it's much simpler. So here's what we will do. You're going to dynamically track the best path and the score of the best path from the source node to every node in the graph. At each node, you keep track of the best incoming parent edge, the score of the best path from the source node to the node through this best parent edge, and eventually compute the best path from the output to the sink. So here are some. We'll actually go through it a little bit. The notation. I'm going to use this notation. Y is the probability. T is the probability assigned at time t. And S of R is the rth symbol in the target sequence. Not the alignment, but the target sequence. I'm using the uppercase S. So here, this is S2, this is S1, this is S3, right? And you can have, for example, in B phi, S1 is E and S3 is also E. So some symbols can occur twice. And now, at the very first instant, I'm only allowed to go start at the top left. So I don't have to worry about the parent for the top left. There is no parent. The parent is a null. So to the top left, to that one guy, I'm going to assign the score of the probability of the symbol corresponding to the first, the probability of the first symbol. And for the rest of these guys, I'm going to assign a probability of minus infinity, just so we know those things are impossible, right? And the best parent for the first guy, of course, the first guy doesn't have any parent. Now, as you go down time, the row on top is kind of special because the row on top only has one parent going backwards. So the best parent for the guy on the row on top simply remains row 0, right? And the score is simply going to be the score on the same row at the previous time times the probability assigned to that symbol at the current time. And subsequently, for the rest of these guys, if you look at, say, the second box over here, for the second entry, you would choose amongst the two parents at the left, the parent with the higher probability, in which case this is going to be the top one. And once you chose it, so this is either going to be the previous row, if the best parent in the previous row scored more than the best parent in the current row, or it's going to be the best parent in the current row, right? So you just store a pointer to it, and then subsequently you just extend the probability of the best path to the best parent by the probability of the current symbol. So that way what has happened is now you have the best path to this guy, and you also have the probability of the best path to this guy. Everything is stored. And then you can repeat this for every other symbol in that column. Of course, the black dot guys are going to get minus infinity, horrible scores because they only have invalid parents. But then in the next row, you do the same thing. The first row is special, but for the subsequent symbols, you're actually at each symbol you're going to be picking the best parent. You compare both parents, pick the best one, and extend it to the current node. And now you're going to be storing the probability of the path, best path until this node at the node, and just scroll down through all of the nodes, right? So you do the same here and down below and so on. And then you could repeat the process going through time, where at each time for each node, you pick the best of the parents, store a back pointer to the best parent, and extend the best path score to the best parent with the probability of the current node, and store that at the current node. So when this whole thing is done, eventually you're going to get at the very end the best path to the final node, bottom right node, from the source, and also its probability. And since you've actually retained the backwards pointers from from each guy to its best parent, you can actually work your way back and say you can recover the alignment, the best alignment, by just following these arrows backwards. You start from here, go to its best parent, its best parent, its best parent, its best parent, and so on, and just work your way backwards. You're going to get the entire alignment, right? So simple enough. This will eventually give you the expansion of the simple symbol sequence, which aligns the input to the target symbol sequence. And so now, the inevitable pseudocode. So now we've actually found this extended symbol sequence. And now that you've found this extended symbol sequence, you can use that newly aligned symbol sequence as the target and go back, compute your divergences, and you can train. And so the divergence, of course, is simply going to be the sum of the divergences across all time, assuming this newly aligned symbol sequence to be the actual target. And you can compute the rest of the derivatives as before and proceed. The overall training algorithm would something like this, look something like this. You'd initialize your alignments for every single training instance. And once you initialized it, you would train your models with these initial alignments, use this model to go back and recover the alignments for all of your training instances and repeat the process till the whole thing kind of converges, right? Now, this kind of works. There's a problem with this, and this problem is it's going to be, and you can do this in multiple ways. You can train a model and then just compute the alignments for your entire training set and go through the process, or you can do something like SGD, where as you keep updating your parameters, you always compute the alignment using the latest model parameters. All of this is fine, right? Now, the problem here is the approach depends heavily on the initial alignment. If my initial alignment is completely rubbish, then this guy is not really going to give me, it's very quickly going to fall into a black hole. It's going to give you bad estimates, right? And the model is going to be bad. So solution, I don't want to commit to an alignment. When I actually choose an alignment, I'm saying this is the alignment, and then I'm training a model to that alignment. Then I'm using that trained model and finding a new alignment and saying this is my alignment. And at each point I'm committing to an alignment and I'm training for that alignment, right? And if I have a lousy alignment at some point, which is likely to happen particularly in the initial phases of the training, then the whole network can get the whole training can get sidetracked. So the real issue again is that at each time we are committing to the best estimated alignment, which is the most likely alignment, and this can be off, and it can lead you down the garden path. So here is a solution. There's a different way of looking at this. In this graph, there are an exponential number of paths, right? And every path has a probability. So I can think of this as being a probability distribution of all of the paths. And we are just picking the most likely path. Alternately, you could have been drawing randomly from this distribution. And if you are drawing randomly from this distribution, you wouldn't necessarily be picking the most likely path, but you're committing to one of these paths, right? And picking the most likely path is like always selecting the most likely path. So if you take this probabilistic view, again, so for instance, you have these alignments. Let's say you have just 2-time instance, 3-time instance. So you could have AAB, ABB, right? So these are the 3 is not enough. 4. So I have x1 through x4, and I'm looking for the symbol sequence AB. Then the possibilities are ABBB, AABB, AAAB. I have these 3 possibles here, and each of these has its own probability, right? And what we are really doing is picking the most likely. We are just picking this guy because it has the highest probability. An alternative view is to say I'm going to be randomly drawing from this distribution, where I will pick the more likely ones more frequently and the less likely ones less frequently. Or I can take one step back and say, since I don't really have complete confidence in any one of these alignments, I'm not going to pick any one. I'm going to use all of them. If I use all of them, what exactly would I be doing? What I would be doing is I would be computing the divergence between the output y and ABBB. I'd be computing a different divergence between the output y and AABB, and the divergence between y and AAAB. I'm considering every possible alignment. But are all of these alignments equally important? Not really. The one that has higher probability is to be trusted more than the one that has lower probability, right? So what I will do is to take the sum of all of these guys, but it's a weighted sum, and the sum is going to be the probability of A, B, B, B given my input, and so it's not just the input. The information I'm being given is the input itself and the fact that the final target sequence is AB, right? The final symbol sequence is AB, plus P of AABB given XAB plus P of AB AAAB given XAB. Do you see what I'm doing over here? I'm considering every possible alignment and not committing to one alignment. And I'm computing a divergence for every one of these guys. And then I'm taking a weighted sum of all of these divergences. And that's what we will be minimizing. And the weighted sum of all of these divergences, the weights that you're going to be applying to any one alignment, is going to be the a posteriori probability of that alignment given the current model. Right? What is the problem with doing that? There's something even more mechanical, right? How many such alignments exist? So you can't really be doing this explicitly, right? But this is what we are going to do, and we're going to exploit the structure of the problem. So what we will do is simply observe that this is simply the expected divergence between the output of the network and an alignment, and the expectation is over all possible alignments. And so basically, what is the divergence itself? Now look at, if I'm using one-hot representations, then for the target output, if I have a given alignment, then the divergence is going to be simply the negative of the sum over all time instance of the log of the probability assigned to the target symbol in that alignment by the network, right? This term is the divergence for a specific alignment, where in that alignment the symbol assigned to time t is st. We're just going to take an expectation of this guy over all possible alignments. Yeah? And expectation is, you're looking puzzled? No, okay. So expectation is linear. I can move the expectation in, right? So which is going to be the sum, and now suddenly I went from summing over an exponential number of terms to going inside and having a sum over t of a small number of expectation terms, which makes things a lot more convenient, right? And furthermore, at each time, I'm going to be looking at the expectation of the divergence at that time over all possible target symbols. So what does this really mean? Now, this guy, what is the expected divergence between the output of the network and the target symbol, where the target symbol can be one of those four guys, B, E, F, and E, right? So if I actually write this down, this is simply the sum over all of the target symbols of the probability of the symbol given everything that we know, which is the final compressed simple symbol sequence and the input, times the log of the probability assigned to that symbol by the network. Right? It's mechanically explained, but the concept is obvious. So you're going to say, what is the probability that this symbol is in the alignment? I'm going to use that and then multiply that by the divergence that I would get if this symbol was in the alignment, right? And then for the next guy, I'd say, what is the probability that this second symbol was in the alignment? I'm going to multiply that by the corresponding divergence and go on. And in each of these cases, the divergence is simply going to be the log probability. So that's what using the one-hot representation gives you this very nice convenience, right? And so this problem now reduces to computing this a posteriori probability term, which is the a posteriori probability of finding a symbol, probability that a specific symbol S occurs in the alignment at time t, given everything. This becomes the real problem. Now, what is that probability? So this term over here is the a posteriori probability of having a specific symbol in the alignment at time t, without considering anything else. Correct? So that probability is going to be proportional to the probability of the entire graph, entire subgraph that goes through the node that corresponds to having that particular symbol at time t. Right? So this guy here, which is the probability that the alignment contains at time t contains the symbol SR, given everything, is simply proportional to the probability of all paths that go through symbol SR at time t, which is the specific highlighted blue box. Make sense? Right? And once you state things in this way, then things become really trivial to compute. You can compute that, yes.
What's the difference between the two probabilities?
Which one? The first one is given S, the second one is and S. So in the first case, you're guaranteed that the alignment lies within that box. The second case is the probability that, of the box getting an alignment within that box and that specific, the box is the entire graph, and that specific symbol. Now the reason this is different, the reason you have to consider this is that if you just compute the total probability of all paths through this graph, is it going to be 1? Not really, right? The total probability of generating any symbol at any time over the input is 1. Here this is only looking at a subset of the symbols. So the total probability is not going to be 1, right? So you have to subject it. So you're constraining it to being within that box. So instead of making it conditional, I've just moved it onto the left-hand side. That's all. But the arithmetic of it is not. Does that make sense? Right? I mean, the only probability that you're assigned. So what the network actually produces is, if you have many symbols, say A, B, C, and D, it actually produces probabilities for each of these guys. at each time. Correct? And you can have any number of paths through this guy, through this. And the total probability of all of these paths is going to be 1. But then if you say I'm only allowing myself the specific symbol sequence AB, then the reduced box that you're pulling out is throwing away most of these paths. So the total probability is going to be less than 1. Right? And when I say I want to be within that box, you're conditioning it on the extra information that you provided, that it's within that box, right? So anyway, the net is that you're really looking at a probability term which is proportional to the total probability of the subgraph that goes through the specific box, specific node that represents having a specific symbol at a specific time as part of the alignment. So here, for instance, this blue graph is the total probability of this blue graph is the probability of all paths that align vector, the input vector 3 against the first instance of the symbol E. Right? Now, computing this probability, it turns out, is fairly straightforward. I'll skip the arithmetic and I can restate it like so. The total probability of that graph is the total probability of the subgraph that's enclosed in the blue box times the total probability of the subgraph that's enclosed in the red box conditioned on the blue box. This is just straight up Bayes rule, right? So we'll skip most of the math on the slides. You can go over that later. But now here's something that happens. If you look at the difference between the previous figure and the current figure, and the previous figure I have 2 arrows going from the red box, from the red subgraph, from the blue subgraph into the red subgraph, right? From the left to the right, I have these 2 arrows. I can actually ignore those. Ignoring those is the equivalent of saying I'm assuming conditional independence. What do I mean by that? It says that the probability that vectors number 4 through 8 are going to be aligned to one of the paths in the red graph does not depend on how the first 4 vectors are aligned. This is the conditional, given that everything must live within the big box, right? This is what conditional independence means. And why is conditional independence usually even meaningful in this particular context? Conditional independence is meaningful because we're using a neural network. And think of how the neural network operates. You have some input. From the input you're computing hidden outputs. And the output probabilities at each time only look at the hidden outputs. They don't look at the outputs at other times. H is deterministically computed from X. So Y depends only on H, right? And therefore, the output at time t doesn't affect the output at time t plus 1 if H is fixed. Which means that the symbols that are likely to be output in the second half of the sequence don't depend on the symbols that were output in the first half of the sequence if H is fixed. And H is fixed is X is fixed. The input is fixed. So you have conditional independence. And because you have conditional independence, you can sort of chop the arrows between these 2 subgraphs and compute the probabilities of the 2 subgraphs kind of independently. This is an assumption. Now, if the output were feeding back into the network, then this assumption could not be made, right? So now, this means I can write the probability of the total subgraph that goes through the specific node we are looking at as the product of the probability of the graph shaded in orange and the probability of the graph shaded in blue. 2 separate graphs, right? And the first guy, I'm going to call this my forward probability because I'm going from left to right. And we'll see why we'll call the second graph the backward probability. But let's focus on the first term, which is the forward probability. Okay? The forward probability is the probability of all paths, all ways of align. So the forward probability at time t to symbol r is all ways of aligning input 0 through t against symbols s1 through sr, which is the total probability of the graph that is actually exposed in the figure. Right? Visually it's got to be obvious. And now here's the little recursion that pops out. This probability, the total probability of the entire subgraph that ends up at y3e, is going to be the total probability of the subgraph that ends up at y2b and extended to include y3e, plus the total probability of the subgraph that ends up in the green box, y2e, extended to y3e. Because the graph that ends at that final node is an extension of one of these two subgraphs. Right? So basically I can say the probability, now if I'm going to represent this term as alpha. Alpha TR is the total probability of the subgraph that starts at 0, 0 and ends up at symbol SR at time t. So over here alpha 3e is going to be the probability of that subgraph, which is going to be the probability of the subgraph ending at 2b with y3e at 2b times y3e. So you're basically extending that to this guy. So the probability of this subgraph times the probability of this symbol plus the probability of this subgraph times the probability of this symbol. Make sense? Right? All I'm doing is sort of extending the paths. And this guy over here, if you look at this subgraph, the total probability of this subgraph over here is simply the alpha term over here, which is alpha 2b, right? The total probability of this subgraph, including everything ending here, is simply the alpha term over here, which is alpha 2e, right? And so this entire formula can be written as alpha TR, alpha 3e is alpha 2b times y3e plus alpha 2e times y3e, right? Or more generally, I can write this as this: the alpha at any row r at any time t is going to be the sum over all of the predecessors, the parents of the TR node of alpha t minus 1 parent times the current probability. Very simple recursion, right? Makes sense to everybody? So now this recursion, so to explain carefully, this is the actual formula. It just collapses to one simple formula which says alpha TR, because here there are only two incoming paths to any particular symbol, right? So any symbol has only two parents. So alpha TR is going to be alpha t minus 1 r plus alpha t minus 1 r minus 1 times ytsr. That final y is common to both, is commonly multiplied to both, right? And so here's how you'd actually perform the computation. At time 0, you're going to set the alpha 0, 0, which is the top left box, to have just the probability of that symbol. The rest of the alphas, of course, in the first column have 0 probability out here. And then subsequently, we're just going to go through a simple recursion. So here's how it goes. At time 0, you're going to assign the probability to the top left box as simply the probability of the symbol that's in the box. And the black dot boxes are going to have probability 0. Then at subsequent times, you're just going to go over for the top row. I keep treating the top row especially, but because the top row has only one parent. But for every other row, you're simply going to be summing the alphas immediately to the left and the alpha immediately to the left and one above, which are the two incoming paths, and then multiplying that by the probability of the current symbol. And you do this for every symbol in the column. And you can keep doing this going forward until you've computed the alphas for the entire graph. At this point, you have the alpha for every single node in the graph. So there's some pseudocode here. But what we've done in the process is to actually compute this first term. We decompose this total probability of the probability of the total probability of the shaded graph, or both the into two factors. One is the orange shaded portion, one is the blue shaded portion. And we've computed the probability of the orange shaded portion, which we've called alpha t, which is this first guy, right? So I can just replace this by alpha t. And now we actually have that alpha t for every single box, no matter where. You know how to compute that alpha t because we've computed this for every box, every node in the graph, right? I can use the same logic now to compute the second term, which we will call the backward probability. And we represent it as beta t. So beta tr, now here is the interesting thing. Beta tr is the portion of the is the probability of the subgraph that follows tr. It doesn't include tr. Is the portion of the subgraph starting from tr till the final node, but not including tr. So over here you can see the blue path doesn't actually include the index that's actually the actual term that's being indexed, right? So clear? And now, so beta tr is the probability of the exposed subgraph over here, but not including the orange box, because the orange box is already accounted for when you're going forward, right? And so that I can decompose. The total probability of the exposed subgraph is the probability of the subgraph starting in the green node plus the probability of the subgraph starting at the red node. Exactly the same logic as before, right? And the probability of the subgraph starting at the green node, each of these guys I can say is I can pull out the probability in this box over here outside, which is to say now this is the probability of everything, this portion of the graph times the probability of this node plus the probability of this portion of the graph times the probability of this node, which actually came out, right? And now you can see exactly how the recursion works. This guy, the probability of this portion of the graph is basically the graph that starts from this node and goes to the final node, right? That's the beta for this guy. Similarly, this graph is the beta for the second guy, right? And so this simply became over here y4e beta 4.1 plus y4f beta 4.2. Yeah. And so I can generally write every node has two children, right? I can say that the beta at any tr position tr is the probability of the symbol immediately to the right times the beta computed one symbol to the right plus the probability of the symbol to the right and below times the beta computed at that point, right? And now each beta is being computed in terms of the beta ahead of it, right? So you can't actually compute this left to right, you have to compute this right to left, which is why we call it the backward probability. So the general notation, the beta tr is going to be the sum over all the successes of the tr node of the probability of the successor node times the beta computed at that point. And the way you would do it, you would start off at the final node and you can compute the beta for the bottom right node very easily, which is simply going to be 1 because everything that follows it is 1, and you cannot have any subgraphs following the blackened out node, so the beta for those guys is 0. And now I can keep going backwards, and at each point I'm just going to be computing as I go back. This is, I just recursively we have the edge case, we just recursively use the formula that we just saw to compute the beta for every entry in the column using the betas in the next column. And so I would compute the beta for the first column and the second one and the second one, and all the way to the beginning, right? So the pseudocode again, as usual. So in the process, we have also figured out how to compute this. The beta probability is the probability of this blue subgraph. Yeah.
Could we not just flip it up, down, left, right, and do the same thing we did for alpha for the beta?
You're just not going to be using the final probability, right? So here, when you compute the beta for a specific box, then the beta for that box, it doesn't include the probability for that box because that was computed using the forward pass, right? You can do it by flipping it and doing it, but then you'll have to divide, you'd have to remove the unfactor the probability of the corner box itself, because now it would otherwise it would end up being multiplied twice. And in fact, in practical implementations, that's exactly what they do. So you write one code, use it twice, and then divide out the unnecessary extra term. Yeah.
What is the beta for the bottom right? I didn't actually.
That's 1. It just means the probability of everything that follows here, right? So the probability of the subgraph, there is by setting it to be 0 to the top guys, you say that you can have no successor. But for the bottom right guy, given everything that you have so far, the probability of the successor is just 1.
And alpha for the top left?
Alpha for the top left is literally what is the probability that the first symbol came from this box, which is simply going to be the probability of that box itself, right? Beta is everything that follows. Alpha is this probability of the box itself, right? So in the process, we have computed both of these guys, the alphas and the betas. And so now we can actually compute the posterior probability for the node. The product of the alpha and the beta at any time is the total probability of the graph that goes through that node, right? So I can compute this for every node in the graph, but the sum of those 4 is not really going to be 1, because the sum of those 4 is going to be the total probability of the entire graph that we've just drawn. You divide it by the total probability of the entire graph, that's going to give you the conditional probability of each of those nodes. And so you can compute the probability of a symbol S, SR at time t, given everything, which is the target symbol sequence and the input, as the product of alpha and beta at that time normalized by the products of alphas and betas for every node in that column, by the sum of the products of alphas and betas for every node in the column. Because you're looking at conditional probabilities, right? We are saying what is the probability that the symbol at time t was SR. So if SR goes through the entire set of symbols, these probabilities must sum to 1, correct? Meaning this posterior probabilities within any column must sum to 1. And so what this is doing is making sure that the posterior probabilities, the normalization, makes sure the posterior probabilities within any column sum to 1. Questions? Right? So we have actually managed to compute the gamma term, the posterior probability term, for every node in the graph. And there's the inevitable pseudocode. So now the expected divergence is very straightforward. The expected divergence was the sum over all terms, time instants, of simply the expected log likelihood for every symbol, where the expectation was taken over the posterior probability distribution. That simply works out to the weighted sum of the log likelihoods at the negative weighted sum of the log likelihoods for every symbol at time t, where the weight itself is simply the posterior probability gamma, right? So now we've managed to compute a divergence, and the divergence takes some dynamic programming, but it computes the expected divergence between the output and the alignment over all possible alignments. So instead of committing to a single alignment, they have explicitly factored in every possible alignment where every alignment has been factored in with a weight, which was simply the posterior probability of the alignment. So we've gone through several steps of computation, but the final formula ended up being really simple. And now I can compute the divergence, right? I can compute the derivative of the divergence. The derivative of the divergence with respect to the output at any time yt is going to be zeros for all the symbols that are not in my target output. But for the symbols that are in my target output, it's simply going to be the derivative of this divergence with respect to the probability assigned to that symbol. So for example, if I'm looking for, if I have, if I'm looking at B phi, right, then the derivative of my divergence at time t is going to have this form. So let's say I have all of these phonemes B, E, for, and maybe T, L. I can have a bunch of phonemes, right? This didn't occur in the sequence. This didn't occur in my sequence. This didn't occur in my sequence. I'm only going to have derivatives at these three locations. And the specific locations are, and those specific derivatives are going to be, this guy is going to be the derivative of the divergence with respect to the probability assigned to B. This one is going to be the derivative of the divergence with respect to the probability assigned to E, and so on. Right? Yeah. If E occurs 2 times, you will sum the probability. So here, observe that if a symbol, now these derivatives must be computed from here, number 1. And secondly, you also get this issue that if a symbol occurs multiple times, then you have to sum over all the instances that it occurs. So here, for example, the symbol E occurs twice, right? So if I want the derivatives on 2 different rows, so if I want the derivative of the divergence with respect to the probability assigned to E at time t equals 4, I must compute the derivatives with respect to the values in each of the 2 boxes, and then add those guys, right? So at this point, we have reduced the problem to that of computing this particular derivative. How do I compute the derivative of the divergence with respect to a simple probability, right? That's simply going to be this guy. This is what you really want to compute, right? So, which is the divergence, of course, was the weighted sum of these terms. Since you're looking for the derivative with respect to the output at a specific time, the summation over time went away. You're only interested in a specific column, right? And you're going over all of the rows which invoke that particular probability and computing the derivative of the term that contributed to the overall divergence by that probability. And we know what this derivative is, right? This derivative is very straightforward. The derivative of this is just using straight up derivative rules. If I want to compute this guy, that's simply going to be gamma TR divided by the probability. And remember that gamma itself is a function of the probability, correct? So you want a second term, which is the derivative of gamma with respect to the probability times the log probability term. Now it turns out that computing the second term is a little more tedious, but there's an alternate explanation we can say, which says that we are trying to perform maximum likelihood estimation. And if you make that claim, which is a perfectly valid claim, you can get rid of that second term entirely. And the derivative simply becomes this one simple term, which is the derivative of, which is simply gamma divided by the probability, right? And so what has happened in this process is that we have nicely sort of figured out how, so we've defined a divergence, which was the expected divergence over all possible alignments. And we've also figured out how to compute the derivative of this divergence with respect to every single probability term output by the network at each time. Which means now we have the derivative of the divergence with respect to yt at each time. And this can be used to, in further back propagation, to compute all of the parameters of the network. Right? And so here's the overall training procedure. The problem, you're given an input and output sequences without alignments. We want to train models. You're going to set up the network, typically a many-layered LSTM. You're going to initialize all of the parameters of the network. And then for each input, you're going to compute this forward pass, which gives you this table of probabilities. And then for using this table of probabilities, which is you're going to construct the graph which represents paths through the target sequence, because you really have to restrict all the computation to this graph, correct? And then subsequently you perform the forward backward at each time to compute alphas and betas for each row at each time. And then you compute the gammas, and then you can compute the derivatives of the divergence with respect to the yt's at each time, right? And so this derivative, of course, is going to be the value that we just saw, where the derivative of the divergence with respect to our probability assigned to any given symbol at any time is simply going to be the gammas, the sum over all the rows that invoke that probability of the gammas for those nodes divided by the probability, right? And then this is for a single input, you'll be aggregating this for all of the inputs in your mini batch and updating your parameters. So the story so far, sequence to sequence networks which irregularly output symbols can be decoded by Viterbi decoding, but they require alignment of the output to the symbol sequence for training. And training can be performed by iteratively estimating the alignment and then time synchronous training. Alternately, it can be performed by optimizing the expected error over all alignments. And that is going to be far less prone to local optima and such like, particularly when you don't have too much training data. Right? So we will continue with this in the next class. And like I said, this is the longest lecture. Instead of just flying through it, I'm going to take my time about it. Was there something else that I wanted to? I don't recall. We're out of time, so I'll stop right here and take questions, if any. Yeah.
Question.
Yeah.
So for each of those sequences, we need to construct a table for it.
Yeah.
During training.
Yeah. So the point is, if you look at the pseudocode, right? The pseudocode does something interesting. It doesn't explicitly construct the table. I have actually written, for instance, for the forward algorithm. Let me see. I wish my laptop were faster in responding to things. Takes a lot of time. So I call this a simple backward algorithm. In every case, I've got the simple version and the complex version, right? In the simple version, look at what we are doing. We are going through the set of symbols in the output. N is the number of symbols in the output. You're pulling out the row corresponding to that symbol. And you're creating an explicit table which just includes those rows, where some rows might occur multiple times, right? But it turns out you don't have to do it explicitly, because when you actually look at this guy, STI is simply going to be YT S of I, right? So instead of explicitly creating this table over here, I can directly refer to the original Y's itself, like so. Where this bypasses the explicit construction of the table. But implicitly, yes, we actually construct that table. This is to make sure that you don't get rubbish alignments. There's a second question. Somebody had a question? Yeah.
Did you solve the problem of having two consecutive same expected output?
That will be in the next class, right? It doesn't. We solve the problem of not having alignments, but then we still have the issue of having multiple expected outputs. We also have the issue of how do you actually decode things, because remember, our standard Viterbi decode only gives you an approximation, because it gives you an aligned output, whereas you want the most likely order aligned but not time synchronous output, right? And so to account for that, we have to sort of modify our decoding algorithm. So we have these two issues left. We'll look at these in the next class.